So in part D, we have the derivative of the definite integral. Both lower and upper limit are in the function form, and the function for this problem or the integrand f of t is the natural log of the t. So with the fundamental theorem of calculus part 1, I set on a side it in the form of d by dx integral, the constant term. Over here, the lower limit must be the constant. It could be negative, positive, or zero. Doesn't matter as long as it's the constant because based on the area function, that's the left end of the bound of the area. So definite integral from a to the x, the function f of t with respect to t equals the function at x. So based on that, so we're gonna have to bring the number as part of the integral. Again, it could be starting at any point. So I'm gonna choose the number one. The reason to put in number one. So for this problem, it doesn't matter. You put one or negative or zero. But in general, if you really look at the computation, at some point, the natural log of the one, you can find the value. The natural log of the negative number is not defined by the restriction of the natural log itself. Okay, don't worry too much about that. So as long as you pick any constant, that will be fine if you work on the fundamental theorem of calculus part 1. Okay, so for this case, I'm gonna pick the number. So choose a equals 1. That means I'm gonna break it up as the the point in between, or kind of break it up as the integral, as the sum of the two integrals. So this will become d by dx. The first part integral e to the x to the number 1 of the natural log t with respect to t plus another integral like from 1 to e to the 2x natural log t with respect to t. So when we break it up like this, we can apply the fundamental theorem of calculus part 1 for each definite integral. I can use this method because this is one of the properties that we saw at the end of 5.2. Like um, when you have the definite integral from point A to point B, you can split it up as A to C plus integral C to B, where C is somewhere between, or as a joining point. Okay, as we split them as the sum of the two definite integrals, we just work on each one and make sure it fits into the form that the lower limit is a constant, the upper limit is the function. The second definite integral is already good because the lower limit is already in a constant term. The upper limit is in the function. So we leave the second integral for now, but we work on the first one because the lower limit is not the number yet. So we have to flip it. What I mean by flipping, like we're gonna swap lower limit and upper limit. When you when you swap the lower limit and upper limit, what we have to do, what the property that we use, if we swap, what's going to happen to the definite integral?
Change the sign.
Change the sign. So we're going to apply the negative sign to the first definite integral. Thank you, Jeff. And then I write it in the form that we can see each one in the form that's similar to the fundamental theorem of calculus part 1. So just write it as derivative of the definite integral. So now both of them are in the right form. The number as a lower limit. So the upper limit of the first one, we see the function e to the x. So we're going to treat this as, I'm going to write it as u1 and the e to the 2x as a u2. So we see u1 as a function of x, u2 as another function of the x. Then we're going to apply the chain rule for each one of them. So I put on the side here, since my u1 is e to the x, so the derivative of u1 with respect to x, which is the same as e to the x, right? This is the one of the convenient function that the derivative and the function itself are the same, while u2 is e to the 2x. So then the derivative of u2 with respect to x is 2e to the 2x because we apply the chain rule as e to the power of the function 2x. inner function is 2x. So we apply the chain rule like the derivative of the outer multiplied by the derivative of the inner. Some of you missed using the chain rule from grading your work from the exam 3, so be careful. Um, so now the first one, we apply the chain rule by doing as a derivative with respect to u1, integral 1 with the negative sign, right? This up until u1, the natural log t with respect to t, and then multiply by the derivative of u1 with respect to x. The second part, it becomes the derivative with respect to u2, the integral from 1 to u2, the natural log t with respect to t, and then multiply by the derivative of u2 with respect to x. Just do the double of what we did in the similar to the last example. So the first one now becomes um, since the function is natural log t, right? We're gonna replace t with the u1, and u1 is e to the x, so it becomes natural log e to the x, and then multiply by the du1 dx, which is e to the x. I put parentheses because I don't want you to get confused with the e to the x here and e to the x here, because the first e to the x together with the natural log. And the second part is the natural log of the natural log of the t, but t will be replaced with the u2, so it's going to be e to the 2x, and then multiply by the derivative of u2 with respect to x, which is 2e to the 2x. We are done applying the fundamental theorem of calculus part 1. The next part, what we have to do is just to clean up, to simplify it. Okay, I'm going to add one more slide here just to clean up what we have. From negative natural log e to the x multiplied by e to the x of the first one. And the second is the natural log e to the 2x multiplied by 2e to the 2x. So apply the natural log and exponential property. When you have the log and the exponential together, since both of them are inverse of each other, so the first part there, it can be simplified to be just x, okay, with the negative sign and e to the x. Similar to the second term, the natural log and the e reduce, and actually you can use the power property of the natural log, then the natural log of um, b to the power r is r times the natural log of the b, and recall the natural log of the e is 1, so kind of multiple properties that we can use to simplify the numbers. The last, or the simplify the expression, and the last portion still multiply by 2 times e to the 2x, and simplify one more time the step by step. We have negative x e to the x plus 4 times x times e to the 2x. And if you want to simplify more for this problem, you can do more and more and more, because you can apply multiple properties to get the problem less complicated. So we can factor the x and e to the x out, and then we get negative 1 plus 4 times e to another x, because note that e to the 2x is e to the x times e to the x. When you multiply the same base number, you add the power together. So that's why we can factor one of the e to the x out. So this is one of the solution forms, or one of the most simplified solution form for part D, or the last example.